Here we go, moving into section 7-5, entitled Proving Triangles Similar. So we've discussed some ideas of congruence and similarity between polygons. And now we're going to move on to proving, at least in this case, proving that triangles are similar using some properties that we've learned, including some things about parallel lines. So let's begin with the check skills you'll need. Number 1 is vocabulary review. And this says, if two triangles are similar, then their corresponding angles are blank. And their corresponding side lengths are blank. All right, so here we have two triangles. And let's assume these two triangles are similar. And we're supposed to fill in the blanks here. Then their corresponding angles are blank. And their corresponding side lengths are blank. So let's consider these two peak angles, the ones up at the top. Those two would be corresponding angles in this case. And what could we say about those corresponding angles? Well, we know their measurements are the same, and a fancier vocabulary term for that is just congruent. So we know that if two triangles are similar, then their corresponding angles are congruent. Right? We can imagine a larger version of each of these triangles, a smaller version of each of these triangles. But as we dilate them, as they get larger or smaller, their angle measures stay the same. And so these are called congruent angles. Now we're also asked to identify some information about their corresponding side lengths. So if we consider, let's consider this side length and this side length. And so it's probably becoming more apparent to you now that I've written in some measurements. So if this side length on the left triangle is 4 units and the side length corresponding to it on the right-hand triangle is 2 units long, you understand that, let's assume this, if this side length were 2 units long, you know intuitively this side length is also going to be, well, half of 2, 1 unit long. And if you recall, the word for that is proportional. Meaning that if we take a side length over its corresponding side length, in this case 4 over 2, that will equal the ratio or the fraction written between these two corresponding side lengths. 4 divided by 2 does equal 2. 2 divided by 1 also equals 2. And therefore if, let's say, this side had a length of maybe 2x units. So we have a variable and we're unsure of the exact length. 2x, well, this one would be then half of 2x, or just 1x units long. Number 2 says, if a square with a side length of 6 inches, is a square with a side length of 6 inches similar to a square with a side length of 10 inches, explain. To answer this problem, let's consider 2 squares. Maybe in your head visualize, or take a look at the squares I've given you. A square with a side length of 6 inches similar to a square with a side length of 10 inches? Well, one is just a dilated version of the other. And so yes, these are similar. Notice that they would all have, corresponding angles would be congruent. They're all right angles anyway. And then corresponding side lengths would be proportional. More specifically, each of these sides measures 6 inches. And each of these side lengths, and I'm only labeling 2 for example, measures 10 inches. So sure enough, 6 over 10 will equal 6 over 10, which will equal 6 over 10, which will equal 6 over 10. So no matter what, because squares are just dilated versions of one another, they will always be similar. So with that in mind, let's move ahead. It says what you'll learn in section 7-5 to determine measures of the angles of triangles and use them to help prove that triangles are similar. Why learn this? Architects and engineers often make use of triangles when designing buildings and other structures. 3 copies of the same triangle have been arranged as shown. Lines L and M are parallel because their alternate interior angles are congruent. The angles labeled in blue show that angle 1, angle 2, and angle 3 form a straight angle along line L, which means that the sum of their measures is 180 degrees. Therefore, the sum of the measures of the angles of each of the triangles is 180 degrees. And finally, a key concept. The sum of the measures of the angles of any triangle is 180 degrees. And that comes directly from this information in the Why Learn This. What this means, and this is kind of a fun activity to do on paper, is if we take a triangle with angles 1, 2, and 3, and we remove those angles, literally tear them off if we're doing this on paper, or here I've taken screenshots of each angle, and then we arrange them so that they're adjacent to one another, meaning they all share a ray, then they will add up to a straight line. And with the magic of digital media, I've been able to join these three angles together for you to show you that indeed angles 1, 2, and 3 form a straight line when added together, meaning that the sum of their angles is 180 degrees. And there's nothing special about this triangle I've constructed. This works for all triangles, right? Triangles, obtuse, acute, scalene, equilateral. They'll always add up to 180 degrees, and so that's a property of triangles. The interior angle sum, which is a fancier way of saying the sum of the measures of the angles of any triangle, is 180 degrees.